Hi. So I've decided for this next project to build a 2D plotter for the Texas Instruments TI-99 for a computer, primarily to essentially print the high-resolution screen on paper. Um, and the primary drive for this whole thing is my long-standing interest in mathematical graphics, aptly described in this excellent book by Robert Dixon called Mathographics. This is a Dover edition, and I would highly recommend trying to get it through Amazon or eBay or other such outlets if you can find it, and if you have an interest in such things. The majority of this book deals with pen and paper and compasses and rulers in order to draw complex mathematical shapes. However, there is a section in there with tantalizing graphics which uses computer algorithms, gives you an outline of an algorithm, and you can adapt it to your particular needs on your particular computer. And so I really wanted to draw things like that, for example. Um, although it's probably pretty ambitious, but like a spiral, for example, or something of the kind. Really, the limitation is primarily that low resolution of the computer, but nonetheless, I think it has a lot of promise. So here we go. So for the mechanical construction of the XY plotter table, I would be using two sets of these. Um, this is a kit that comes together, and I have another one packed still yet. And basically, I found those on Amazon, and they should provide most of what I need at the base to build the table, um, along with two very popular and very inexpensive NEMA 17 stepper motors. They're each about 10 bucks or so, and a couple of brackets for them and some screws. Most likely I'll end up needing some additional 3D printed parts, particularly for the pen holder, but we'll see where the design takes me. I haven't yet decided on a permanent design as of yet. I've been scouring the internet and YouTube for ideas, and there are quite a few different ways of doing this. So we'll see what I settle on, and we will go from there. So here are some of the support structures that I'm 3D printing. Here we're doing the coaster wheel with its bracket and the pen holder. So here's the final mechanical assembly of the plotter table. The green parts are the 3D printed parts that I needed to support the assembly. And as you can see, we have overlapping structures here. This section here is for the X movement component, and when we move it, you can see the platform move in the X direction. The stepper motor would be here, and then this part here, platform, supports the Y component in this movement direction, and we can see move in the Y direction. And finally, we have the pen holder assembly. This is the the content of an old DVD-ROM drive, which I've shown before, and I'm using its stepper motor assembly. This is not a high torque assembly, but that's really not needed for pen control. All it needs to do is go up and down a little bit. This is the 3D printed pen holder. It's essentially just a hole with a set screw. The V shape here helps keep the pen in a vertical and secure position. Really simple design. And on the front here I have a free coasting wheel assembly. and that was needed because if we look at um, the Y component of the table, the stepper motor will be sitting here, and as we move uh, the pen holder assembly forward, this part here started to sag because there was really nothing to support it. I mean, I'm using fairly stiff birch plywood, quality plywood, with minimal flexing, but even then there was a little bit of sagging at the end. And what would have happened if I didn't put that support wheel up front was that the print would have gotten denser as we moved forward, because the pen would be pressing harder on the paper. So it's a really simple wheel. I mean, just essentially a disc, and with a support bracket which is glued to the edge of the Y assembly, and it works just fine. Really, when we move it, I mean, it just does the job. Last thing here, I did add limit switches to all the movement sections. So here's one for the pen assembly. Basically, when the pen assembly goes down to a certain point, it'll click and it'll indicate that we're at the end of travel. Same thing for the Y component here, and there's another one here for the X component. So combined, these will allow me to essentially bring the assembly to its point of origin and initialize it. Okay, so that's basically the end of the mechanical part of this project, and it was really fun to build, actually. Took a bit of time, but it works. So next step is to finalize the control circuitry and the software. More to come. So moving on to the control circuitry for the stepper motors, here's my test bed for a single stepper motor. I'm using a 4-wire bipolar stepper motor, which I recovered from an old printer. And all the gory details of the circuitry can be found in my blog, and there is a link in the video description to it. But essentially, as an overview, bipolar 4-wire stepper motors have 2 coils in them, and in order for them to move in a stepwise fashion, you need to control the polarity of each coil in a specific sequence, and that means that each coil will require reversal of polarity in a cyclical fashion. In order to reverse the polarity on a motor or coil, you need to use something called an H-bridge. And given that we have 2 coils in this motor, we therefore need 2 H-bridges, and you can see the 2 of them over here. I should mention that there are specialized chips that can do all this control stuff. But since I had the parts on hand, I thought I might as well just build the circuit with discrete components, and it's kind of fun. The H-bridges are controlled with inputs to the transistors, and depending on that input, the polarity to each coil will be either positive or negative. There is also an additional component right here, which is the 74HC595 chip, and it is essentially a serial to parallel shift register chip. And what essentially happens is that you can input a byte serially, and it will present that byte in parallel at the output pins. In order to control the 4-wire stepper motor, you only need essentially 4 output pins from the chip, and therefore with one chip we should be able to control 2 stepper motors in total. For the entire project, what we will need then is 2 H bridges per motor, so we need an additional 2 here, that's 4 H bridges. And then I'm thinking of using an H bridge for the pen up and pen down functions. Remember, we have an x-axis, a y-axis, and then a pen up and pen down function. So that last function will require a stepper motor and therefore 2 additional H bridges. So in total 6 H bridges and 2 74HC 595 chips will complete the circuit. All this will find its way on a homemade PCB, which will make it far more compact and far less messy. The control is coming from the parallel port on the TI, and you can see it over here. This is the breakout parallel port. It's connected to the back of the TI-99/4A computer. This is a handy little device which I use quite frequently because it allows me easy access to the pins of the parallel port, and therefore much easier to use with external circuitry, at least during the testing phase. Alright, and it's running right now. Another thing I need to mention is that the circuit needs to be powered externally. It consumes about 135 amps. Let me see if I can. There we are. This is the current requirement by the circuit running currently. It's about 135, 136 milliamps. Although once you turn on the circuit initially, it'll spike to close to 200 milliamps. Therefore, this is clearly beyond what the TI-99/4A parallel port can source, and so it is imperative to use an external power supply. At this moment, I am using a homemade, basically scratch-built 5-volt power supply. But for the larger motors I'll be using in this project, I will definitely need to use something a bit more sophisticated and likely current limited, because some of these stepper motors can have very low coil resistance and can draw quite a bit of current in a matter of seconds, which can fry your circuitry or your computer. So here's the stepper motor in action, and let's see if we can focus better. There we are. As you can see, it'll turn in one direction, then it'll reverse and turn into the other direction. Very simple. This is, by the way, being controlled using the rich extended basic language on the TI-99/4A computer, and this is probably as fast as I can run it. So clearly not fast by any standard, and there's a very good chance I will need to use assembly language for the final product. But for demonstration purposes, this works just fine. So here's the completed controller board, and it's got 3 L298 dual H-bridge controller chips and 2 74HC595 serial shift registers, which basically convert the serial input into a 8-bit parallel output. And the whole thing is controlled via the parallel port of the TI-994A. This is the breakout box connected to the to the parallel port, and here are the control pins that I use, and that basically is the whole design. And here's the plotter all connected, looking pretty. So yeah, basically everything is done, and at this point we are gonna go ahead and do a printing test. Okay, we're ready to start printing here. I have a piece of paper stuck to the corkboard. Notice that this paper is actually much larger than the printing area. The printing area is limited by the screen resolution of the TI-994A computer, which is 256 by 200 pixels. Also, I'm not printing in continuous lines simply because resolution is so low that continuous lines result in very jagged lines which are very unsightly, and instead I'm using discrete points which give much more pleasing results. So let me go ahead and run the complex sine wave program here. So first thing it's going to do is going to initialize the plotter and home the axes so I can place the pen in the holder. This has to be done in order to position the pen properly. As you can see, it's quite loud, and that's because the stepper motors are not running really at optimal speed, secondary to the limitations of the extended basic environment, which is controlling the machine. Of course, I'm using assembly language subroutines as support, but still, the whole thing is pretty slow. So I'm going to go ahead and put the pen in, and it's a pretty clunky affair. Here we are. So press a key. Okay, so it's done, and it's going to finish and home in here. Alright, so that's a complex sine wave. So overall looks pretty good, seems to be doing what it's supposed to do. Great. So I've decided to overlay an Archimedes spiral on top of the complex sine wave, just for the fun of it. And the spiral is supposed to show uniform spacing between the branches, but because of the variability or I should say the play, especially in the y-axis, it does cause some significant variability. I mean, the overall shape is correct, but as you can see, for example, over here, the spacing narrows a little bit, and here you see it's wider than here. These are unfortunately the mechanical limitations of this design and the quality of the components used. In a future project, if I ever want to do this again, I definitely would use a different type of design, probably a bridge type, rather than this overhanging type, which is much more unstable. So we'll let it run here, of course. It takes quite a bit longer than the sine wave, because there are a lot more points to plot. Alright, so it's basically done. Notice that it clips the edges here. That's because it won't print obviously outside of the printing area, otherwise we could damage the mechanisms. Well, yeah, I mean, it's a pretty presentable result, I would think. So really that's the end of the project at this point. I'm pretty pleased with it. There are other ways to go with this. I mean, additional things. I'm going to be playing with it quite a bit, trying to create some more interesting mathematical graphics and such, because this is really what started the project in the first place. So anyway, I hope you enjoyed this as much as I did. Again, all the gory details of the design and build are found in my blog, and there's a link in the video description. Thank you for watching.